Okay, let's get going. So we're talking about milestone 4. We've been talking about different algorithms for a few days now. Hopefully, we're going to get through the last ones today. Okay, so we were talking about iterative algorithms last week. And in iterative algorithms, we're changing the solution pretty quickly, trying to find a better delivery order. So we have to, I've been drawing solutions on the screen, drawing out how does this delivery route look, and clearly we can't do that in our computer program. So we need to think of how are we actually going to represent this path that our delivery person is going to follow. So one way we could do it is we could store the whole solution. So if you read the milestone 4 header, you'll find that the way you have to return your solution is shown here. You have a vector of what we call Courier subpaths. And a Courier subpath is just this little structure. I've had a few questions from people about what is a structure. Does anybody want to tell me what the difference between a structure and a class is in C++? So let's see, so C09, I'm going to go to you. What's the difference between a structure and a class? You got to, wait a second, let me turn your mic on. My bad.
So struct is by default copy, but class is by default parameter.
Perfect. Okay, so exactly right. So don't be confused by struct. Same as a class, just default, everything is public instead of private. I'm doing that for many of these data structures because we're not trying to have any abstraction, I'm not trying to hide what's in them, so it's easier just by convention, we often call those structs to say it's all public. Okay, so this Courier subpath that you have to return, we got a vector of them. Every one of these subpaths basically looks like one of your milestone 3 solutions. You have a start intersection, you have an end intersection, and you have a vector of street segments to go from start intersection to end intersection. So that's no accident. It's going to be kind of convenient to use your milestone 3 solution to hook up these different intersections. Okay, but our traveling courier solution is bigger than our milestone 3 solution. It's not just one of these paths from some intersection to another. It's a whole bunch of them to make a whole delivery route. So maybe my start intersection is 53, my end intersection is 28, and I've got all these street segments in between. That's a subpath. And I have to make a whole bunch of those to return as my solution to this traveling courier problem. Okay, so we've got M places we can pick our truck up at, so M depots, and we've got D deliveries to make. So D pickups, D drop-offs. And let me just cycle through this. So this is a particular solution. And one courier subpath would be like this green section. Okay, so it went from a certain intersection start, a certain intersection end, and all the street segments in between. And you have to return a vector of those. You have to return a bunch of them to make the whole thing. Okay, so you could write your code to just, as you're evaluating different orders, maybe you shouldn't go from here to here. Maybe you should instead go from here to, I don't know, maybe over here, okay? As you're evaluating those different delivery orders, you could maintain this whole solution, but it's a bit inconvenient, okay? So it could maintain the whole thing and just work with it all the time. But yeah, that's a little more bookkeeping than I'd like to do. I'd like to be able to change these delivery orders really fast, look at many different options. So can I do this better? It'd be better to have a more compact representation. And a more compact representation would be, I'm going to store just the order of the deliveries, and only when I have to. So when I'm returning my final solution, maybe if I have to compute travel time, I have some good reason to turn it into a full solution, only then will I turn it into a full solution. So this should be faster and easier to change the order of my deliveries, and that means I'm going to be able to look at more options. Okay, so let me show you what I mean by that. Okay, so let's see, this is the same solution I had before. That's the full solution. And let's see if I can get this out of the way. Okay, that's good. So sounds looking good. Instead of representing, the whole travel path, all these street segments, everything, as I'm optimizing, I'm going to make something simpler. I'm going to make a vector. Whoops. So I'm going to make a vector, and that vector is going to be of type, it's a type I defined. Okay, so I'm going to make a structure called pick or drop. And I'm going to make a vector, I'll call that the object that I just made delivery order. And here's what my delivery order might be. Okay, so I'm just showing graphically that in this structure, I've got two things. I can have a pickup intersection, I can have a drop-off intersection. And I make a whole bunch of them. So I say, pick up something for item 0 in delivery order, drop off item 0 in delivery order, pick up item 1 in delivery order, pick up item 3, drop off item 3, drop off item 1, pick up item 2, drop off item 2. Okay, so my delivery order is very compact. It's basically just storing, what am I talking about? Am I talking about a pickup or a drop off at every entry in this vector? And which one am I talking about? What index is it in the order I was given for this problem? I was given, maybe in this case, I was given 4 deliveries to make. So my vector just says, first thing is a pickup, and it's index 0. It was whatever was the first thing in my input. Second thing is a drop off, and it's also index 0. It's the first drop off in my input. Next thing is index 1's first pickup. Next thing is also a pickup, but it's index 3. Okay, so this is a pretty succinct representation. So my code can change this much faster. Does this make sense? People understand how this works? Seeing lots of blank stares. So do you understand? So it's just a vector. It's a vector basically of what's next. So in my structure, I could basically have a bool saying, am I pick up or drop off? And an int, which is, what is my index in the delivery order that was given to me? And that's enough for me to store, well, what am I doing next? It's not the only way I could do this. I could actually just store the index of the intersection that I'm going to, and whether it's a pickup or drop off. But basically, I'm storing the solution in a much more compact way than storing the whole vector of street segments. Sound good? I'm going to take that as, okay, I can see how I can code it. I'm not showing you all the code for it, so you have to decide, okay, how am I going to turn that into code? Okay, I haven't put the depots in. So for the depots, I could store them as well in my delivery order. So I could make this structure that I've created, instead of having 2 different things that I could store in every single entry. So right now I might have a bool that says, are you a pickup or are you a drop off? I might make what's called an enumerated type, like just basically I can give it different values. I could say you are a depot, you are a pickup, you are a drop off. I could use magic numbers like 0, 1, and 2, but it would be better for me to define an enumerated type where I can say you are a pickup, you are a drop off, you are a depot. And my struct's not just going to have what's the type of the next thing. It's also going to say, well, which one is it? If I was given 50 deliveries to make, it's going to say, well, you are a pickup and you are pickup number 3. So that's the type I'm storing in my vector. I need to store a whole vector of those. So that I give the order in which I'm going to do these deliveries. Okay, so let's see, what does that look like? Let me see if I can move this little zoom bar out of the way. And let's see if I'm actually recording too. Okay, that's good. So yeah, this is what my delivery order might look like now. So I've shown pickups as being green up arrows, drop-offs as being blue down arrows, and depots in purple. So this just says I'm going to start at depot 0. I was given a bunch of depots, start at whichever one was in the 0th entry in the vector you were given. And I'm going to end on depot 2. And in between, I'm going to go make all these deliveries. Okay, so giving the indices of which pickup or which drop off in my input am I doing next. So this is still pretty succinct. Okay, and it now has a complete solution. It's got the depots in it. Now, I don't actually have to store the depots. Okay, the reason I don't have to store the depots is it's important I store the order of the deliveries, because that's what I'm trying to optimize. There are a lot of different ways I could go through these deliveries. Some of them are much, much better than others. So that's what I'm searching for. I got to store that somehow. The depots are actually a bit simpler. I'm always going to take, if this is the first thing delivery I make, I go to the pickup for whatever delivery 0 was, then I should always start on whichever depot is closest to that. Okay, so this was my first pickup, my first thing I'm going to in terms of delivery. This is the depot closest. I will always do that. There's no reason not to. When I drop off, I wound up at the end here. Okay, so that was my last drop off. I said I'm going to drop off delivery index 2. So in my input in index 2, there was some drop off. That's the last thing I'm doing. I will always go to this depot then, because that depot number 2 is closest to that. So I've stored that in my solution representation, but I don't actually have to. So you can store the depots if you want, but you don't have to. You can just fill them in at the end. So you could say, this is how I'm representing my solution, just this middle part. I'm going to optimize that. And whenever I need to get a travel time, the routines that figure out travel times, they'll just figure out which depot is closest to each end, and they'll add that into the travel time. But I'm not actually even going to store it. So either of those is a reasonable way to do this. I mean, I personally like to do it this way, because my solution representation is kind of as succinct as I can make it. And when I need to go get a travel time, just the code that has to figure out the travel time of the whole thing just has to be a bit smarter. It has to add in whichever depot. Okay, so I think I've got a question. So go ahead.
Okay, so for our conclusion for this milestone, do we only need to provide the order, or do we have to provide the detailed path?
Yeah, good question. So you in the end have to give me the full path result, okay? Not just the order, the actual path result. But because if you're using relatively advanced algorithms, if you're using iterative algorithms that are actually going to change things a lot, like the ones we talked about last week, those algorithms work better if your solution representation is compact and they can change it quickly. So it's better if those algorithms work on a more compact representation, decide, oh, let's make a change here. Let's change this, the order of this and this. And let's, as fast as possible, figure out, is that legal? Is that fast? If it is good, we're going to change it. And only at the very end is it going to expand that solution into the full path. So you have to do it eventually, but you're going to save a lot of CPU time if you don't do it at every little step in the middle. Does that make sense? Yeah. Now, if you have a very simple algorithm, you might just say, it doesn't matter. My algorithm's still simple. I'm just going to fill it in the first time because I never change anything. And you could do that. But if you want to get better results, having a more compact representation that you can change and evaluate perturbations to is going to help you. So yes, that's a good question. Okay, so with this new representation, so I'm showing you how you can store this. I mean, I'm not writing you the code, but I'm showing the symbols that you can easily turn into data in a structure and make a vector of that. Let's just look at how our permutations that we talked about last week work. So this delivery order that I'm drawing here, represents the path down below. So I'm not storing the depot. I said we'll always just assume we start at whatever is the closest depot. I'm not storing the end depot. We'll always go to the closest depot to the end. But I do store that I'm going to go to this pickup intersection, then pick up. Basically, I'm going to go to the first pickup, then I'm going to go to the third pickup, then the second pickup, okay? When I say first, third, second, it's like those are the indices for those pickups in the input vector I'm given, okay? So that's the way I'm choosing to refer to them. So, and then I have to go do all the drop-offs, etc. So I've got a complete order here, and that order matches what I've drawn. So one of the perturbations we talked about was to swap the order of 2 deliveries, okay? I think 2 of the ones that we talked about swapping were this one and this one. So what do I have to do to store that new delivery order? Not much, okay? So if I want to swap these 2 drop-offs, all I have to do is find them in my delivery order and just swap them in the vector. Okay, so visually, I'm reconnecting things like that, and I've now changed my delivery order, but in terms of what I change here, it's just a very small change. I change that I was gonna do drop off 0 and then drop off 2, and now I'm gonna do it in the opposite order, drop off 2 and drop off 0. So that is just a swap of a couple of entries in a vector. It's gonna be fast. Okay. Now, I should also have some routine that can take this delivery order data structure that I made and compute a travel time quickly for it. Because once I've made this new delivery order, the next question I'm going to have is, well, how fast is it? So I want to quickly be able to look up what its travel time is, and in this case, it's 72. And I can decide whether that's better or worse and decide whether to keep it. Okay, so that was swapping the order of 2 different intersections. That was a pretty simple perturbation operator. Another more powerful one we talked about was 2-opt. So 2-opt, remember it disconnected our path. It removed 2 edges in our path, and then it reconnected things in a different order. Okay, so we're going to delete 2 edges in the path. Let's say I delete this one and this one, okay? So in my delivery order, that corresponds to, I'm going to cut there between drop off 1 and 3, and I'm going to cut here between pickup 1 and 3. Okay, so I'm just denoting that by putting bars in. Now I got to reconnect them in some different way. So my code should let's try reconnecting this differently. Okay, so to reconnect them differently, here's one way I could reconnect them differently. I could go from this pickup to that drop off. Okay, and I could go from here to here. So I've now reconnected it in a different way. Some of my path doesn't make sense. You can see I'm not going around in a consistent direction. So between these 2 cut points, I'm basically now going in the wrong order. Okay, so I have to reconnect this path properly, I actually have to reorder the piece in the middle. Okay, so I reverse those deliveries. And now I've got I've got a logical delivery order again. Okay, so for 2-op, the general procedure is you need to pick the order in which you're going to reconnect these 3 subpaths. So you pick 2 cut points, that divides your path into 3 subpieces. You pick what order you're going to put them back in. There's no right or wrong. Perturbation operator just kind of tries things. You can reverse a subpath or not reverse it. So it's your choice of whether you do that or not. And you check if it's legal. Okay? So we can calculate, well, how many of these 2-ops can we do? So let's say we've got D deliveries to make. D is around 100 for a big problem. There are pickups, there are drop-offs, so we've got 2 D kind of nodes we're connecting together. So that means the number of edges or connections between them is 2D minus 1. So how many different 2-ops can we do? Well, we can choose 2 edges to cut. That's how we're going to disconnect them. So if D was 100, we can choose 199 times 198 pairs of edges. The order doesn't matter, so we divide by 2. So about 20,000 ways, 20,000 pairs of edges we could choose from for a problem that size. That divides our path into 3 subpaths. We can reorder those in 6 ways. So we can choose, we got 3 subpaths, we can put them in any order we want. And then for every one of those, we can choose whether to reverse them or not reverse them. So that's another 8 options. So it means we can basically, after we've cut up this long path, we can reconnect it in 48 ways. So in total, that means there are about 1 million 2-ops that we could do for a problem this size, which is a lot, but fast code can try them all. So you can actually write code, it'll try all those options and just say, Most of them will be bad ideas. It'll say their travel time's worse or they're illegal, it's not a good idea, but some of them will probably wind up being good ideas, and you can get improvements by doing them. If your code is fast, you can just try them all. If you find an improvement, it means you actually changed the path. So some of these perturbations that you tried that weren't beneficial now might be beneficial. So you might actually want to try them more than once. If your code's fast enough, you just try them all. And if you made any changes, you say, well, let's go back and try them all again. And keep doing that until you run out of time or you give up. You just say, it doesn't seem like I'm finding anything good. Okay? These aren't the only perturbation operators. So there's another classic traveling salesman a perturbation operator called the 3-opt. And a 3-opt basically cuts not into 3 pieces, it cuts in 3 places. Cut path in 3 places and reconnect. So a 2-opt basically cuts it in 2 places and reconnects. A 3-opt cuts it in 3 places and reconnects. So it's more powerful, gives you more choices of how to connect things together, but it takes longer to explore them. There are now a lot more choices. A lot of 2-opts in the problem we're giving you, because you have to pick things up before you drop them off, but a certain pickup you must pick up before you can drop that package off. A lot of 2-opts, like ways you can reorder your delivery, will actually be illegal. Okay? So that means you might prefer to look at perturbations where you kind of didn't cut huge parts of the path. With a 2-opt, you're cutting a path in 2 places. You might decide, I want those 2 places to be only a few deliveries apart. Because if they're too far apart, I've cut my 100 deliveries into 3 pieces of 33 each, the odds of me being able to reorder that and still being legal might be really low. So you might say, I don't want to do those really big perturbations, it's too disruptive, so I prefer to do small ones. Maybe I just swap 2 intersections, or maybe I make 2-opts, but I try to keep the 2 cuts, 2 places I disconnect the path close together. You could also try re-legalizing. Okay, so I've been describing code where you just perturb the delivery order somehow, and then you check if it's legal. And that's perfectly fine. But you may, especially with more complicated perturbation operators, a lot of the things you do are probably going to be illegal because you've changed the order so much that something becomes illegal. You're trying to make some pickup or some drop off before it's pickup. You can change your perturbation operator to fix that, okay? At least you might fix some of the obvious cases. And I'll leave it for you to think about that. You don't have to do that, but it's a reasonable thing to think about. If you're getting a lot of illegal perturbations, you go, I'm wasting my time. Maybe you can make a perturbation operator where you actually try to fix it up. I've got these pickups that are occurring after their deliveries. Maybe I should change the order to move them earlier. And therefore I'll evaluate that. That's like a fixed up delivery order. It's now legal. Maybe it's a good one. And there's lots of things you can come up with. So you can try coming up with all sorts of your own ideas. You don't have to, relatively simple algorithms can get a pretty good answer, but if you're trying to get the best answer, coming up with smart ways to perturb the solution can be very beneficial. Okay, so that's it for kind of iterative exchange. I know it's kind of abstract, a lot to take in, and don't worry, you don't have to do all these different things. These are just ideas of ways you can explore. Any questions on any of that? If not, I'm going to kind of take a step back, try to give you an overview of some of these heuristics. Okay, I'm going to take that as I'm good to go for a step back. Okay, so one way you can think of what we're doing is we've got this complicated cost space. Our cost is travel time. We're trying to find delivery orders to minimize travel time. And there are many different solutions, and I'm drawing them here in a kind of one-dimensional space. But in reality, for the big problems we're giving you, this is like a 200-dimensional space where you're deciding what order to do things in. But I can't visualize a 200-dimensional space, but it's a lot bigger. And the height here is the travel time. So where it's high, that's a bad solution. Okay, and where you have a spot where all the solutions around it, you just make a little change, they're worse, that's called a local minimum. Okay, little changes don't make it better, they just make it worse. And the spot where the travel time is the best is the global minimum. So, okay, so there's only one of those. It's really hard to find because it's a really big search space. But there are lots of local minima, and some of them are pretty good. Finding a good local minima is a pretty good answer. Remember, this is a computationally hard problem, so nobody knows how to find this global minimum and guarantee they found it in a reasonable time. So we're settling for just try to find good local minima. If we actually by accident happen, well, if we actually happen to hit the global minimum, fantastic, but we'll never be able to prove we hit it anyway. Okay, so what are our different algorithms doing? Okay, so the first thing you could do is just pick a random order. Just take the deliveries in the order we give them to you and just hook them together with your path plotting algorithm and return it. It's actually not a bad thing to do. It gets you a legal solution. You can go, hey, I'm legal, I'll get some marks, and I know my code works. But it's likely to be quite bad. So we're in a huge space with many, many different solutions, and most of them are bad. So if you pick a random order, you're probably way up here. Pretty bad answer. Okay, so one of the heuristics we talked about was multi-start. So multi-start just says, try again, change something. So if our solution's random, that just means pick another random solution. And we can generate random numbers in a computer, so we could produce a whole pile of random solutions. We could check if they're legal, and if they're legal, we can hook them together and say that's our answer. Okay, so instead of one now, we're picking a whole bunch. And then we compute their travel time, and we take the best one. Okay, so now we're gonna get this one. That's the best of our 4 random orders. It will be better, probably still not very good, because there are so many solutions in this space. Even if we randomly select 1 million of them and take the best of it, it's better than picking one, but it's probably still not that great because the number of solutions we calculated a couple of days ago, and it was unbelievably huge. Okay, so we can do a greedy algorithm. So a greedy algorithm, kind of makes intelligent choices about what to do. So it tends to be pretty good. It's a lot lower down on this cost space, especially if we coded up a pretty reasonable greedy algorithm. It's got some smarts to it. It's still not locally optimal. Okay, like there are still small changes we could make that could make it better. And that's true, well, for greedy solutions, certainly for this problem. Once you get the greedy answer, because it's kind of just making what seemed like the best decision one step at a time. At the very end, you can look at it and see sometimes it's made some mistakes. Okay, we can do iterative improvement. So iterative improvement, it's a pretty good idea to start with a good solution. So if we've got a reasonable greedy algorithm, that's like our starting point. Get that solution, and now we can try changing things. Swapping deliveries, using 2 ops, using our own perturbation operator, whatever we want. And we can try a whole bunch. Some of them are worse. Okay, so here I perturb something, I calculate the new travel time, it's worse. I don't want to do that, so I throw away that solution, go back to my greedy one. But I try a different perturbation, and that one's actually good. Okay, it reduced my travel time, so I like that, I'll keep that one. And then I can try again, try some more perturbations, and I find some more good changes, and I keep taking them, and I get down to this local minimum. Okay, so it's a local minimum, and an iterative improvement algorithm can find that because it's making small changes. It's searching its local space, looking for ways it can fix things up. So it's gotten us to a local minimum, which is pretty good. Okay, so we could combine this with multi-start. So if we combine it with multi-start, we're basically gonna do the same thing I just showed. We get our greedy solution, we use iterative improvement to improve it, we get down there. And then it's hard for us to get out of here. Okay, we're kind of stuck in that local minimum. Any little change we make doesn't make things better. Don't know what to do. Maybe we still have some CPU time. We try we keep that solution. It's good. We don't throw it away. But we now try, let's make a new greedy solution that's different somehow. Let's improve it. We get here, we get stuck, not better. But then we try another one, we get there. Try another one, we get there. And we're going to take the best of all of these. Okay, so in this case, the first one we did was the best, but in some cases we might have gotten a better answer by trying multiple times. Okay, so local perturbations, I just showed you this, you will generally get stuck, right? So we go from Here's maybe our initial greedy solution. We do local permutations, we can get to here, but we won't get to this spot. It's not too far away, it's better, but to get there, we'd have to make some changes that are not good, right? That would increase our travel time first. Okay, so any local change we make just doesn't look good. So we're kind of stuck there. And let's say that those local changes, so let me show that to you again. But those local changes I'm showing you here are just swapping two deliveries. So they're kind of pretty small changes. They move us a little bit, not too far, and we're stuck. If we coded up some larger permutations too, like those two ops that I showed you, which are a bit trickier to code, take a bit more CPU time, and a lot of them aren't going to be very good ideas, like they're not going to get gains, but they basically make bigger changes. So they can actually jump all the way from here over to here. Okay, and now once you've done that, you can find more local changes, you can get into this deeper local minimum. So if you have some more powerful perturbation operators, you're less likely to get stuck. Okay, but you do have to be careful because what makes them more powerful also makes them less focused. They tend to jump around a lot. A lot of the things they propose may not be very good ideas. So you could run out of CPU time as well. You might find that you're wasting your time kind of looking at low probability things and never look at the high probability. So having some changes that are very focused and some that are bigger can be useful. So actually E07, can you guys quiet down up there? Thank you. Okay, there's another technique called hill climbing. Okay, so hill climbing means you actually make the solution worse for a little while in the hopes that you will eventually get to a better spot. Okay, so I started off, let me show you it again. I started off here with this yellow solution. It's pretty good, and I can't improve it with any local operator because they all look worse. But despite that, I just go with it for a while. I make a change and the travel time gets worse. I make another change, the travel time gets worse again. But now I make a change and it starts getting better again. Okay, and it keeps getting better for a long time as I make changes, and I get all the way down to, okay, I obviously faked this slide, but I get to the global minimum, right? So hill climbing can get us unstuck. And it sounds counterintuitive. We're actually making a change that makes things worse, but we're gonna just keep trying it for a while to see if it gets better again. You have to watch your CPU time when you're doing this. You're making things worse for a while. You have to explore, see if they get better again. That all takes more perturbations, more CPU time. So if you run out of CPU time halfway through it, it's not very beneficial. Okay, so there's a balance here. Okay, so hill climbing is, we've talked about kind of 4 heuristics now. So we talked about greedy algorithms, multi-start, iterative improvement, and now hill climbing. So hill climbing is a way to get out of a rut. I'm stuck, all my local changes are not improving things, so we're gonna change something, even if it looks like a bad idea at first, and we're gonna see if things get better. So for our problem, hill climbing would change the delivery order, even though it increases travel time. So it's just a perturbation, but we accept it even though it's worse. Now, it's a good idea if you do this to save your best solution first, because if you go off and keep perturbing things and it doesn't get better, you're going to want to go back to it. Okay? But if it does get better, you can do local perturbations around that new solution, keep exploring, and you eventually can find something better. If you don't, so maybe you keep making perturbations for some amount of time and it doesn't get better, you can go back to your safe solution. Okay, so it costs more CPU time, but it lets you explore more options. So it is a trade-off. So this is a little bit like, okay, so if you're in a relationship, you maybe think it's not bad, but maybe it's not perfect. So you're wondering, could there be a better match for me out there somewhere? Okay, so hopefully your significant other is an engineer, so you can explain this to him or her in sort of technical terms. You can try a hill climbing move, say, I'm gonna be sad for a while, but we'll break up, date other people, and maybe after dating quite a few other people and so on, I'll find like a better match. So you could do this, but you will be sad for a while. Maybe in the long run, you'll be happier. Now, there's something you can do in a program that's really hard to do in a relationship, which is this piece. You know, can you save the best solution first? So that's a very awkward conversation where you say, well, I want to do some hill climbing for the next year, right? Go date other people. But if it doesn't work out, I'm coming right back. right? Because this is pretty good. But in a program, you can do that. So it's easier. Okay, there are a bunch of different approaches for hill climbing. One of the very powerful frameworks for this is called simulated annealing. It's used for a lot of problems. It's called simulated annealing because it's a computer program style. It's called a meta-heuristic. It's like a style of heuristic that mimics the procedure by which people make strong metals. Okay, so when you're trying to make a strong metal, you actually cool it slowly. Okay, if you quench it, you just take a hot piece of iron and you stick it in a barrel of water, it will be kind of brittle. It's because the atoms didn't have time to find basically a good arrangement in a lattice and a low energy state. Okay, so you gradually heat up and cool the metal, letting the atoms find low energy states to get a stronger metal. Simulated annealing basically mimics this in a computer optimization program, and it's been used for like a really huge number of problems and works quite well for lots of them. So we start with a fairly poor initial solution. That's basically our hot metal. It's not very strong. And we have a parameter in our program called temperature, and it's initially set to be high. We gradually perturb the solution, which is like moving the atoms. Okay, so in our problem, we will be actually changing the delivery order. Moving around some of the deliveries in the order is like moving atoms. And initially, when we're making these perturbations, when the temperature is high, we kind of let lots of perturbations happen, even if they're making the travel time worse, even if they're increasing the cost or the energy of the system. Gradually, we reduce this temperature, and as we reduce this temperature, only perturbations that reduce cost, that make the energy lower, the cost lower, are accepted. Okay, so that's the analogy. What does it look like? So you start with an initial solution. You get this initial solution from any one of the techniques that we've talked about. Could be a random initial solution, could be a solution from a greedy algorithm, could be a solution from another iterative improvement algorithm. You compute the cost. In our problem, the most natural cost would be travel time, because that's what you're trying to optimize. And you set the temperature to be high. What does high mean? Well, that's one of the things you have to figure out when you're tuning this algorithm. It is a more complicated algorithm. It takes more effort to tune. So you shouldn't necessarily go, that was the last algorithm, therefore it's the right answer. It is the most complicated one to make work well. Okay, after we've got this initial solution, we're going to try improving it. So as long as the solution is changing, we're going to do a whole bunch of perturbations. We're going to move our atoms around for a while. And the way that works is we say we're in some state. So it's like a delivery order. We have a perturbation function, and it produces a new state, a new delivery order. We have another routine that takes that state, that delivery order, and produces a cost. In our case, cost is going to be travel time. So we work out what is our new cost, given this new delivery order, and we figure out what's the change in cost. So has our travel time gone up or down, and by how many seconds with this perturbation? That's what we just figured out. If the travel time has gone down, so our cost has gone lower, it's better, and we'll always accept that. So let's say our new state is, we update our state to be this new perturbation state, and we update our cost, our travel time, to be the new travel time. Okay, so far everything I've shown you is just like iterative improvement, right? There's no difference. So simulated annealing just changes this. It adds in this or condition. So if it's better, accept it, update the state. If it's not better, there's some probability we get a random number between 0 and 1. And if that number is less than this exponential, which kind of represents the energy change, we will still do it, okay? I'm going to show you a few numbers to plug in here, because this looks probably a little baffling. You're like, what the heck, where'd that come from? It comes from the analogy to annealing. So it actually comes from physics, basically. Okay, and then this is just the end. So we do many perturbations here. So you might do 100,000 or 10,000 perturbations. And then after you've done that for a while, you say, let's reduce the temperature. Okay, and you keep doing that until, either you run out of CPU time, or the solution is not changing, or your temperature is close to 0. You have some ending condition. And there's no one answer to this. People have researched all sorts of different ways to do this in simulated annealing. So there's no one, oh, that's the best way. There's lots of different ways people do it. Okay, so let me just zoom in on one piece of that code. This was the code where we're saying, let's get a new solution by perturbing the old one. Let's figure out how much the travel time or the cost changed, and then let's decide whether or not we accept it. So if this change in cost is negative, which means that travel time went down, we always accept it, okay, no matter what the temperature is. Let's say our change in cost was 30 seconds, so it got worse. 30 seconds more driving time. If our temperature was 30, our probability of updating is still 37%. You actually plug the numbers into this exponential, you're gonna find you've got like a 37% chance of accepting this. If our same 30-second travel time increase, if our temperature was 10, then we've only got a 5% chance of doing this. So as temperature drops, we're less and less likely to accept large degradations in our travel time. We're getting worried about it. We've got to start getting to the end of this. If our temperature was 3, that same 30-second travel time increase has got almost no chance of being accepted. Right? It's considered such an extreme change at this point with this low temperature, we're not going to do it. And then we lower the temperature again. Okay, so now let's say our temperature goes down to, well, actually, sorry, our temperature's already gone down to 3 degrees. Small changes. Say our travel time is going to get 3 seconds worse. Well, that's still got a reasonable chance of happening. So what happens is simulated annealing will initially allow a lot of hill climb. Things can be allowed to get a lot worse. As the temperature comes down, they only allow a little bit of hill climbing. It can get a little worse, but not big, not really big degradations. And as the temperature gets closer and closer to 0, it basically turns into iterative improvement. You know, it's only going to accept things that are better. Okay, there's a lot of cleverness that goes into this, because this is like just very high level code. So, you know, should you start with a random initial solution or something smarter? For this problem, 50 seconds travel time budget or CPU time budget, probably you want to start with a smart solution if you do this, because a smart solution from, say, a greedy algorithm is a lot better. You know, what should your cost function be? Probably travel time, but you might come up with even some clever heuristics to put into the cost function to help guide things. How high should we set this initial temperature? What do these perturbation operators look like? So just like with iterative improvement, the perturbation operators are really important. In fact, these are generally just the same perturbation operators that we have with iterative improvement, and you can be clever about them. How quickly do we reduce temperature? So there's a lot of tuning to do here. And if you can make these functions fast, if you can actually perturb the solution fast, and if you can work out the new travel time fast, you can do more perturbations. And that gets you to a better solution. You kind of don't have to be as clever about how you adjust temperature and so on if you can just plow through a lot of perturbations. Okay? So, and there's one student a few years ago who, because this was the last algorithm, he was convinced this must be the best one, but his greedy algorithm worked the best for him, because he had a very clever greedy algorithm. And he would post every day on Piazza that the greedy algorithm is better than all the other algorithms. Why did you teach us these other algorithms? So don't assume that just because this is the last algorithm that it's the best. It is a powerful algorithm, but it is also hard to tune, right? So you can easily write this where it's worse than all your other algorithms. Don't do it first, and you may not do it at all, right? The fact that it's last is last for a reason. Okay, so if you want to learn more about algorithms, in next year, you can take EC 345, which is all about optimal algorithms. You can prove they're the best. So examples of that would be Dijkstra and A-star. Those are optimal algorithms. You won't write any code in that course, but you will do proofs, proving this. So if it bugged you, you're like, why does Dijkstra work? You kind of just showed me pictures. You go prove that it works in this course. When you get into computationally hard problems, which is what you're doing in milestone 4, kind of proofs are largely gone, right? You're into heuristics of just things that are shown to work well. We don't have an undergrad course on that. There is a grad course that is about how to apply these complicated algorithms to integrated circuit design. So you can take that in 4th year if you want. And there's another one that's actually, like simulated annealing would be one of the algorithms that they describe in it, and it's actually about how to solve transportation problems. And they actually use the OSM data. So that grad course, you've actually already been doing pieces of. In this one, these bio-inspired algorithms, one of them is simulated annealing. There's another class of algorithms inspired by natural selection called genetic algorithms. I'm not going to talk about them because there's just only so much you can talk about in one course. Those also can be applied to this problem, so they're also kind of interesting. All right, so last few thoughts on this before we close off on algorithms. Time limits. So you got 50 seconds to get a solution. You can get better results with more CPU time in a few ways. You can run multi-start, so you can just run your same algorithm over and over again, changing something and take the best answer. Iterative improvement, you can just keep looking for changes. But for every problem, you've got 50 seconds. So it's going to be hard for you to decide, well, how many multi-starts should I do? If it's a big problem or a small problem, maybe I should do a different number. I don't want to run out of time. So the best way to do this is actually check how much time has passed. And so that's where chrono, you've seen this code a couple of times. We use chrono to time things. So I'm just going to show you all this again. I can define my time limit to be 50 seconds. And I can basically, let me just expand all of this, because you've seen this code before. I can basically say, give me the time right now when my program starts. I've got some optimizer that's going to work for a while. And every once in a while, I'm going to say, give me the time now. And I'm going to check what is the current time. So that's what this is. And if I've used more than 90%, I made up 90%, but I've used more than 90% of my total runtime budget of that 50 seconds, I'm going to stop. I'm going to say timeout is true. I'm going to drop out of this while loop, and I'm going to go finish up and give the answer. So you can write code just like this too. Check how much time is left. Do you want to run one more try of multi-start? Do you want to try a few more iterative improvement algorithms, or do you just want to return the answer? Okay, and this, okay. Last comment, M4 grading. Okay, so there is no user interface, sad to say. You can write one if you want, but and display it in your OP2, but there's no demo, there's no grading of a user interface. I put a rubric on the course website under the assignment. So 25% of your mark comes from getting stable solutions. So solve the problems we give you. Like any one of these milestones, if you read the header file, you'll find it defines a small number of corner cases. If we define them, we're going to test them. So also make sure that you pass the corner cases because we're checking, did you read the header file? Okay. You also want to be Valgrind clean. Okay. So if you're stable, you pass the corner cases, you don't have Valgrind errors, you got 25%. The bulk of your mark comes from your quality. Say quality of results basically is on the big test cases. The little test cases are just there for you to like debug your code. Okay. The big test cases are called hard and extreme, and they have, you know, from about 50 to 150 deliveries. We take the geometric average of your travel time across all of those. There are a bunch of public ones are given. There'll be other private ones that are basically the same, but just different, so you don't overtune. And depending on how good your quality is, that will determine the remaining 75%. There's a leaderboard, so every time you submit, not when you exercise, but when you submit, your score goes into this leaderboard, and you can see how you're doing against the rest of the class. Your ID is anonymized, okay? So you know who you are, no one else does. They just know there's somebody with this score. So you can do it without fear of embarrassment or anything. The top 4 teams will get a bonus of basically on this milestone, 8% to 33%. You know, for fourth, 8%, for first, 33%, which is 1% on the total course to 4% in the total course. Okay, so you can go read the rubric. To kind of turn that into a bit more concrete thing, this is a picture of the leaderboard from early last year. We put 3 solutions that we wrote into the leaderboard. So TA bad basically just takes the delivery order. It's like random. We just connect things in a random order. So it's pretty bad. If you get that solution or comparable to that solution, and you're stable, no Valgrind errors, pass all the corner cases, you get 30% because its quality is pretty bad. TA moderate is some of the simpler algorithms. You know, it's a variation on one of the simpler algorithms we talked about earlier. If you're stable, you get that level of quality, and it's not that hard to code, you get 75%. TA good, we're starting to use some of the more advanced algorithms, iterative improvements and so on. And if you match that and you're stable, 92%. And if you go 5% beyond it, then you're at 100. And then if you become one of the top few in the class, you get bragging rights and bonus marks, okay? So this is intended that you can decide how much work you want to put in this. You like a competition, you're having fun, go for it. If you're like, I got to go work on my other courses, this has been a lot of work, then, go for something like that, okay? And it's, both are going to be fine. And this is in between these numbers. I'm just giving you anchor points. We fit a curve in between these numbers. So it's not like you go, I either get 75 or I get 92. If you are most of the way to this one, you're going to get, most of the way to 92. You just fit a curve in between. And I think that's all I have to say today. So, okay, so that's everything. If you've got any questions, come up and ask me after. What we're going to talk about on Wednesday is multi-threading, which you can optionally use for milestone 4, but you don't have to. But it is an important programming skill, so it's probably good to know what it is.
So the multi-threading, what do you anticipate?